Good morning, everyone. Welcome to CPD for March. Just as always, during the presentation this morning, if anyone has any questions, please just type them into the chat and I'll ask them at the end in a Q&A session. So this morning we've got Kava from Matrix, who is here to talk to us about Adjoint CFD solving. Good morning, Kava. How are you going?
Hey, morning. Pretty good. Yeah, it's a little cold nowadays, but getting used to it, you know.
Especially this morning.
Mm.
Hey, if you're ready to go, feel free to share your screen and then we can just get underway.
Sure, let's do it.
I already know there's a couple of people here at Flight Structures that have some burning questions, so I'll get them to send them through to the chat as well. So you can just have a clear run of presentation and we'll sort that at the end.
Okay, that sounds good.
Cool. Cheers.
Can everyone see my screen pretty well?
Yep.
Okay. Yeah, so we're going to talk about the Adjoint solver today. My name's Kava. Thanks for the opportunity to chat about something that I find pretty interesting and worth sharing. I'll just get into it. Just a little bit about myself. Well, not a little bit, because there's kind of a lot to talk about, because I've moved around a lot and worked at a lot of different companies. I'm originally from the US, started my career working at Honda, working on ATVs, and that was an internship, and then graduated in 2006 and ended up working for Boeing for a few years in Seattle. That was around the time of the 787 program, and did a lot of work on that, as well as a few military projects. I worked for a division inside of Boeing called Phantom Works, which at the time was a central office for advanced simulation. That we served both commercial and defense, and a lot of interesting work coming in the door, because it was mostly the work that was sort of more complicated and too complicated for the program guys to work on. So that was a really interesting experience. Got to go on board aircraft that were being built and experience a lot of interesting, impactful things there. And it was good timing as well. It was right when the 787 was in the thick of development, and so I got a lot of responsibility right out of the gate, and yeah, it was very interesting. But after a few years, moved to Australia, and ended up working for Star-CCM, which is a software company that does FEA software, and mostly serves the excuse me, mining and civil structural industry there. And after about 5 years there, I moved to Germany and learned German and worked for a few really big German companies. One is Vossler Locomotives, doing locomotive design and analysis, a lot of simulation stuff there as well. And then moved on to work on submarines, so non-nuclear military submarines that are produced in Kiel, Germany. And that was a very interesting experience as well. Obviously, got to go on board submarines and work on CFD on submarines and FEA and shock and all of that. And, yeah, very, very interesting work environment. A lot of interesting clients, obviously, interfacing with government officials from different countries and all of that. And it's quite interesting. And then moved to New Zealand and picked up work with EVs Enhanced, which is a company out of Christchurch that builds aftermarket parts for the Nissan Leaf primarily. And I built or redesigned the interior of the Leaf battery pack to include liquid cooling. So a lot of CFD there, a lot of FEA as well, and heaps of design. So done a bit of everything. And now I work for Matrix. So Matrix is a consultancy, and I'll get into that in a little bit. We have a lot of clients all around New Zealand and the world. So Matrix was founded in 1984. That makes it the longest running simulation consultancy in New Zealand. We've got 120 years of collective simulation experience from 4 senior simulation engineers. We offer design, CFD, FEA, and custom software development. We also provide PLM, EDM, and asset management solutions. So that's the other side of the business, about 9 people working on that side as well. Just a bit about what we do in terms of CFD or stuff we have done. Just areas really of interest, plant and process, water engineering, HVAC and clean rooms, marine, aerospace and defense, and general product design. And on the FEA side, plant and process, utilities, marine, including composites, product design, and manufacturing. So we generally pick up jobs that other companies don't feel confident enough to tackle themselves. So we get a lot of interesting work in the door, but that's not to say we don't do the everyday stuff as well. Right, so I'll take a breath here because what is the adjoint solver? So that's the topic today. The adjoint solver is most basically an add-on to CFD. So it's kind of a wrapper around CFD. So it's a method of optimizing flow interfaces, so surfaces that you're wanting to, say, reduce drag on or increase lift on, or both. Basically it takes the flow solution and calculates sensitivities on the surfaces, and we'll get into that later. It's analogous to topology optimization in FEA. So you may have seen already some examples of mass reducing efforts being applied to structures using topology optimization. It's getting quite mainstream now. Back when I was at Boeing in 2007 or so, I remember seeing it for the first time. And back then it was kind of brand new, but now it's even in CAD and everything. So I think the patents have expired or something, and everybody's doing it, so it's quite nice. And I've applied it to giant structure as well on submarines and gotten lots of weight savings out of that. But it's analogous to that in that you're letting the physics guide the solution. So instead of you prescribing the geometry, yes, you prescribe some starting geometry, but then the solver actually uses the physics to guide what that geometry should look like. So it's an optimization technique. And there are three primary approaches. So you can morph an existing mesh. So if you have a mesh or geometry, let's say, you can control it using control points. And then instead of remeshing, you use those control points like a puppet master to sort of tweak the geometry. And the method we're going to talk about today is morphing existing surfaces at every point on those surfaces. So it's a little different because instead of control points, you're actually changing every point on the surface and then remeshing. So it's a bit more flexible because you can imagine morphing a mesh with control points, you might end up destroying your elements and destroying your mesh. However, when you're morphing the surfaces and then remeshing, it maintains that mesh quality generally. You still have to be careful though. And there's another workflow, which is finding an optimal path through a design space. So picture like an exhaust manifold on a 4-cylinder engine. You've got 4 pipes coming into one, and what's the optimal sort of path in a design volume? So that's internal flows generally. So yeah. It's been available since around 2014, but adoption is somewhat slow as far as I can tell, because I guess the workflows aren't so mature and they're a little bit difficult, but also just a lack of awareness. So I think these sort of things tend to flow out slowly into the community, and it takes time for people to give them a go, I think. So how does adjoint technology work? It's pretty involved, but just to keep it simple, the technique we'll be looking at today uses an equivalent spring system, which links the objective function to each surface vertex position. Now those sensitivities, basically it's the rate of change of your objective function with respect to the position in the model of that vertex. And then that's further derived into a sensitivity to mesh deformation in the normal direction of the mesh. So basically what you end up with is a bunch of vectors that show you how sensitive your local vertex position is, or variation in position rather, to the objective function. An objective function can be not anything you like, but there's a range of stuff you can choose, such as drag or lift or or even sort of vorticity and stuff like that. So it's quite flexible, right? So the input is a flow solution, and that defines kind of the spring network stiffnesses. You can think of it that way. And the output is, as I said, a vector field. And so that vector field, you can interpret that as and scale it to simply morph the geometry into a new shape. And we do this kind of over and over again to progressively improve the performance of the structure with respect to the objective function. So if you're minimizing the objective function, you'll be subtracting that vector field from the geometry. And if you're maximizing, you'll be adding to it. In practice, you kind of have to kind of either think about it very carefully or guess and check, is my objective function increasing as I go through the solution, or is it decreasing? I'll reverse the sign of the scaling on those vectors. So that sort of thing. Yeah, so what are the steps? Basically, there's a cycle. So you need a flow solution to run the adjoint solver. So first you solve the flow solution, and that's just a standard CFD run until it's converged with respect to the quantities of interest. And then you run the adjoint solver, and that calculates the sensitivities with respect to the objective function, excuse me. And both of those solvers are iterative, so they're improving the solution with iterations as they go. So it's a bit of a process. And then you scale and filter those sensitivities into displacements. You might want to limit them to some percentage of the scale of the structure. For example, if I've got a 500 millimeter wide structure, I might want to limit the displacement increment to 1 to 2 millimeters. Per cycle, because if you go too far, you can imagine it getting a bit unstable or overshooting that optima that it's seeking. Then you morph the surfaces by those displacement vectors, remesh, interpolate the last solution onto the new mesh and geometry, and then solve the modified flow problem with that initial condition from the previous step. It's worth mentioning that there are other ways to optimize structure. And the traditional method has been parameterization. So you define parameters in your geometry and vary those parameters, and then see what the effect is on your objective function. And from that, you can calculate a finite difference sensitivity with respect to that objective. You need a lot of runs to find the optimal solution in that case, because you need to calculate that gradient for each variable. And some solvers, some optimizers will do multivariate gradient calculations, but they're not very good, and they tend to converge very slowly, if at all. Depends on the package. But typically the number of free parameters is limited, typically less than 10, because the computational expense goes up exponentially with the number of parameters. And so that limits the possible outcomes of the geometry as well. Not just because you have few parameters, but because you're guessing which parameters are important. You're not really letting the solver tell you where to go. The adjoint solver, by comparison, is much more open. So in this case, you're allowing variations at every surface vertex. So every surface vertex is a free parameter. You define the zones where those vertices are, but yeah, lots of parameters. The sensitivity is calculated analytically at every node with respect to the objective function. So there are actually far fewer flow solutions needed as well, because each flow solution solves these sensitivities for thousands of free parameters. And that allows the development of novel shapes. So it allows emergent technology to sort of come out of the physics, which I find very, very intriguing. So we're going to cover 3 examples today. The first one is of a Pitot tube. So the question is, if we start with basic geometry, how much can we reduce the drag on a Pitot tube design? And this is kind of a dumb design, I'd say, because the starting profile isn't any sort of optimized airfoil shape. It's just an elliptical leading edge and a linear body and then a circular trailing edge. So we're going to explore how to make this geometry better in an automated way with the adjoint solver at 2 different flow rates. So Mach 0.7, Mach 0.9, and see, what's the difference between those two, and what kind of gains can we get out of it? So the model is just a small free stream domain with a flat no slip wall, K omega turbulence with an all Y plus treatment to make it less sensitive to the mesh. An ideal gas model is selected, and the altitude's 9,000 meters, and there's about 500,000 cells. And all of the examples in this presentation follow roughly the same order of magnitude of the problem parameters. Okay, so first I ran this at Mach 0.7, and I didn't see a whole lot of gain, and the gain seemed to be somewhat limited. So started out at about 5¼ newtons of drag, not much really already, but got down to about 4 newtons of drag. So about a 25% decrease in drag, which sounds good, but it's pretty moderate with respect to what the solver typically produces. So then I ran it at Mach 0.9. And in this case, I was able to find nearly 60% reduction in drag. I stopped iterations after about 2,500 iterations, just due to time. It was running for a while and I was just getting sick of it. So each of these little bumps, each of these little changes in the drag curve, so this is drag versus iterations, which is just the progression of the calculations. Each of these little bumps is one change to the geometry, and took about 8 minutes on 2 cores. I ran it on our supercomputer, and that took about 48 seconds per iteration or per cycle. So these solutions can be quite fast. That brings them into the realm of practicality for even bigger problems as well. Okay, so this is the initial starting geometry of the Pitot tube. You can see the flow field here. You can see that there's kind of an extensive wake with recirculation and a bow wake as well. You can see this horseshoe wake. And I'm going to cycle through and just go to the optimized geometry and keep an eye on that wake structure as I flip through. So you can see that the wake is almost completely gone. There's a bit of a root wake there as well, hanging on, but the flow is far less disturbed. There's this interesting teardrop shape that forms behind the main forward Pitot tube. And that's a pretty interesting shape. I guess I wouldn't have expected that to emerge, but perhaps it's helping. It's hard to separate what's helping from what's potentially hurting here, but generally I've seen that even unexpected structures like this can reduce drag. So I think if I were to redo this, I would include the forward Pitot tube in the optimization. I guess I was a bit loath to do that because I didn't want to disturb the flow field at the front, but you could also monitor that pressure at the front and make sure that your design changes weren't modifying the read out static pressure. So just flipping back to the original and then back to modified, you can see how the horseshoe wake there shrinks substantially, and the trailing wake as well. And I've got a video, but it's of an older optimization where I even allowed the root radius to change, and it sort of develops this interesting toe shape. Let me show you that. So you can see how the wake is shrinking, but you can also see how the leading edge here perks up. It develops this little toe shape, and back behind that, there's this dip. And it's quite an interesting structure. Definitely open to interpretation. But basically everything the adjoint solver is trying to do is, in this context, delaying separation. So you can see the formation of that teardrop fairing at the back behind the Pitot tube, and also how the structure is sort of thinning out and flattening out to become more aerodynamically, well, to have less drag. Yeah. Okay. Now, when we're optimizing stuff, it's always important to question the robustness of the optima that you've found. So let's say, in this case, we've analyzed two different flow speeds, or optimized two different flow speeds. But what happens if we're off optima? So if we're off of the optimal speed, well, it's interesting because the geometry that was developed at Mach 0.7 ended up giving very little gain in drag reduction at Mach 0.9, but vice versa wasn't true. So in the opposite case, if we took the Mach 0.9 optimized geometry, which had a huge reduction in drag at Mach 0.9, obviously, but it also nearly matched the performance of the Mach 0.7 optimal geometry as well. So in that case, the Mach 0.9 geometry was more robust, was a more robust optimal flow solution in terms of the geometry. And it raises an interesting point, which is that if you're not seeing gains coming in from the adjoint solver, you might want to run your flow at a higher flow speed, exercise that algorithm a little harder, and you might see more gains that also apply to lower flow speeds. But why do we do this? Why do we want less drag? Obviously, at the end of the day, it's about performance. So that might mean for you money, that might mean for you added range. But in the case of a Pitot tube, let's pretend that it's on a 737 and it's got a life cycle of about 75,000 flight hours. In that case, if we do the math, it turns out to save a not insignificant amount of money, so about 45,000 US dollars over the lifetime of that plane. You got to imagine that that's multiplied by that should be also multiplied by the fleet size, and so it does become significant. So little details like this can add up to a lot of saved CO2 emissions and fuel costs. What other things could we have considered in this analysis? I'd say including the flange geometry would be good because it's often quite chunky and not so nice. Be good to optimize that as well. You could extend the optimization region to the forward tubes I mentioned, monitoring the pressure readings, check the mechanical solution to make sure you're not getting too thin, make sure you're not making yourself sensitive to static or dynamic failure of the Pitot tube. And also apply this to worse protrusions. So there's an example here of the SATCOM antenna on a 737. Just looks terrible. Probably a lot of gains to be made there. Could be a lot more impactful than a small Pitot tube. So I'm not sure if you guys have seen the 737 Wedgetail. When I was working at Boeing, it was kind of, I think the development was just about wrapping up, or maybe still something going on there, but I didn't work on it anyway. But the 737 Wedgetail has always kind of bothered me aerodynamically. It's quite an awful compromise in terms of the aero. But obviously it's fulfilling a mission, which is radar scanning, and that's important as well. So what you end up with is a lot more drag than you would otherwise have on an optimized aircraft. So much so, actually, that they even have these spoilers here as well. So it's almost an anti-aerodynamic feature that's a compromise because you have to balance out the forces and moments coming out of this Wedgetail feature. So what I did was I took a model of a 737-800 and trimmed it down to be about the right length and added a Wedgetail feature to it and used that to develop a fluid domain of the top half of the aircraft, including the tail and the Wedgetail. It's a little bit different. You can see that the vector graphic in the back there has a much shorter leading edge fairing on the tail, on the vertical stabilizer, whereas the model that I've built has the stock 787-700 fairing. So altitude, 9,000 meters, just operating conditions for this optimization, Mach 0.78. Here you can see the frontal cross-sectional area of the wedge tail is pretty substantial. And it's even bigger if you were up looking parallel at the thing, it would be even more substantial than that. But you know, it's a significant contributor to drag on the aircraft. So how did the adjoint solver perform? Pretty well this time. Adjoint solver got the drag down by about 50% before I just stopped it. You can see roughly by the slope of this curve. So this is, again, drag versus iterations. You can see by the slope of this curve, the drag's just continuously going down, linearly decreasing until I stopped it here. There's some fluctuation in the force, in the drag force, once I stop it. We'll see an animation of that as well. There's some buffeting coming off the back of the structure, which is pretty interesting. Yeah, so you can imagine if you allowed this to continue running, you may actually get, if just extrapolating, and it's hard to do, but I would anticipate you could get down to 4, maybe 4.5 kilonewtons of drag on that, down from the 10 that it started at. Okay, so this is the original flow field. The contour on the aircraft body is absolute pressure, and the contour on the center line cut field is just velocity magnitude. So the pink areas that's the transparent isosurfaces there. Those are of turbulent kinetic energy, and they serve to indicate generally where wake-induced drag is occurring. So that's the original structure. And I'm going to just go back and forth between original and modified now. So modified is like this. Original, modified. So what you end up getting with the modified geometry is a larger zone of suction at the front here. Low pressure where the flow is accelerating around the front, around the leading edge and turning the corner. And that suction actually has the effect of pulling the aircraft forward. So it's quite a nice feature that the adjoint solver has sort of invented or found there. At the trailing edge, you see a smaller wake structure. Although it's not actually steady, it is smaller on average. So there's original, modified. And I've got a movie as well of this. It's from an older run of this, but I'll show that in a second. Just looking at streamlines, you can see that the original above has just generally a more disturbed flow with some recirculation even in the bow wake there. Never a good thing. And down below, you can see that suction region again that I pointed out. And also just that the streamlines are far less disturbed than the original. Okay. So here's an animation. It starts out with dumb initial conditions, and then the solution settles in as it iterates, it converges, and then gets perturbed. So you can see the flow establishing itself. And there you can see that unsteady wake at the back, how it tends to sort of lick at the vertical stabilizer. But despite that unsteadiness, the adjoint solver was able to find things to change that led to meaningful gains in drag reduction. So this movie goes on for quite a while. You can see it's pausing every once in a while. That's when the adjoint solver is running in the background, figuring stuff out. And then it goes and reruns the solver, the fluid solver. So I'm just going to scan through this and just give you a bit of a sped up version. Keep an eye on that suction zone at the front. You can see how that grows and grows until it reaches roughly where it's going to be. Now I'm going backwards just to see where we started. And forwards again. You can see that the wake gets progressively smaller as the solution progresses. And that's due to all of these tiny changes. Yeah. Now you can't really see the changes here. They're not obvious. Generally, what this solver is doing is making small tweaks to the surface to delay downstream separation. Another interesting aspect is that the adjoint solver isn't compatible with symmetry planes, so you have to use a full model. But at the same time, it won't calculate the sensitivities in a symmetric way within a single adjoint cycle. What ends up happening is you end up optimizing one side of the geometry, then another, and it sort of ping-pongs back and forth. But eventually it converges on a symmetrical situation, if that's ideal. There may be situations where an asymmetric geometry may be more ideal, but I haven't seen a case like that yet. This is a view of the optimized geometry at the top, just to give you a sense of what the style of the results ends up being like. So you can see it's quite wrinkly and the features are quite fine. So actually implementing something like this might be difficult, but you know, with CNC, anything's possible when you're developing the molds to design the structure, but you might not end up implementing all of the features, and we'll talk about that later, but it's interesting to see anyway. Yeah, and the amplitude of these waves is pretty small. This is roughly, I'd say about maybe 5 millimeters or so, or less on this surface. Now the wrinkles on the side at the leading edge of the supporting column and the trailing edge of the supporting column are more substantial. So these bumps are on the order of 30 millimeters, either in or out. And quite interesting, you know, it's quite irregular and organic, and somehow the adjoint solver has found these zones, which, by the way, are self-interacting. So all of these features interact to produce a holistic reduction in drag, something that's very difficult, if not impossible, to do with traditional optimization techniques like parameterization. So let's have a look at a few more areas here, and I'll try to go into depth a little more on these features in a couple of slides. So on the underside of the wedge, let's call it, it's quite interesting. So the structures do emerge as being largely symmetric. There's a little bit of semi-asymmetric wrinkling at the trailing edge. Again, that's probably a flow separation reduction mechanism there at play. I mean, all of this stuff is really. So this is the leading edge, and there are these interesting divots that form, especially where the flow has to separate around the structure or where it has to reconnect at the back. You can see that there are interesting divots that form to sort of allow that to occur with the least amount of drag possible. So the red curve here, so this is a slice of the wedge at the center line. And it shows the red curve, which is the optimized geometry, versus the green curve, which is the original geometry. So at the leading edge, it hasn't changed that much. It's made it a bit pointier, and then rounded off the radii up there to sort of calm things down a bit for the flow. There's a bit of a leading edge bump at the underside, and at the trailing edge, same story, really rounding out that profile. But then there's this interesting nose feature at the back with some quite sharp radii as well, just at the trailing edge. And remember, this is a 2D slice of that 3D structure we saw earlier up here. You can see at the back, the overall, excuse me, let me just change my pointer here. You can see that the overall structure here at the back is quite 3D. It's varying as you go through the lateral profiles of this wedge tail. But here you can see a slice of that seems much more coherent. It's got this separation preventing bulb or delaying bulb at the back. So now we're looking at that wrinkly area that we saw on the supporting column. It's a view from above and a cross section. And again, red is the optimized geometry, and blue this time is the original geometry. What I found interesting about this was that you end up with these sort of sharper radii connected by linear or practically linear regions. I found that quite interesting and unintuitive, but it did lead to a substantial reduction in drag, probably because of the suction that was induced on this surface, this forward-facing surface here. You can imagine if there's a negative pressure here or a suction, that a component of that, let's say let me just see. Let me just draw some force vectors. So component of that, let's say this is the force that's coming off of that surface due to that suction. Well, a component of that is going to be in the forward direction. I haven't drawn that vector quite big enough, but if we just look at the forward-facing component of that, that's going to be reducing drag directly. So that's one mechanism I can kind of understand. It ends up bulbing out here and then going back in to the original aero surface back a little ways. Yeah, so quite interesting. Definitely food for thought there. Trailing edge, somewhat similar, less dramatic changes at the back. What I found interesting here was that generally the adjoint solver prefers subtle changes to dramatic changes. For example, if I were designing this and I had design room to improve it, I might, for example, draw a fairing like this that's sort of tapering back gradually. But the adjoint solver hasn't really done that at all back here. It hasn't really changed the geometry that's sitting in that dead zone of the wake at all. It's focused on sort of the area where separation is occurring. So I thought that was pretty interesting. I guess you could see that as progressively working towards delaying separation, and it might eventually work its way back to develop some more fairing-like geometry, but in this case, it hasn't done that. And you might see that as a bit of a benefit depending on your application. So it seems to me like the best application for this tech would be either early on in the design cycle where you've got a lot of freedom, or even later on where you've got existing structure that you want to make incremental improvements to. Small aerodynamic features, you know, are going to be easier to add to your design just because they interfere less with surrounding structure or internal structure. So, yeah. So substantial savings on this example, because I started out with very bluff geometry and added these fine separation reducing techniques and suction features on the front edge there. And that ended up with a drag reduction of about 48% on the Wedgetail structure itself. What does that mean in terms of money or capability? Pretty interesting, really. If you've got a 7-hour mission, that ends up being a savings of roughly 2.2 tons of fuel. So very substantial amount of fuel that you can save by applying these relatively minor surface perturbations. And again, it's all in theory. Would be great to see this in practice, but I'm pretty confident that you could realize substantial gains. You know, and just gut feeling it, you might add maybe even up to an hour of additional mission time to the Wedgetail by doing that. So I guess that comes with some caveats, though, this sort of theoretical gain, because the radar system might require that there's a certain flatness in front of the apertures. And you know, the starting geometry was stuff that I just reverse engineered it most crudely, and the true Wedgetail design, I'm sure they applied a little bit of aero optimization beforehand, must have. The effect of the geometry changes on the force and moment balances wasn't considered, so you might want to include that. And you can actually include those quantities in your objective function. So you could, for example, say, I want the Wedgetail to disturb the overall force and moment balance as little as possible. And you could quantify that disruption, that moment imbalance, and then minimize that instead of minimizing drag, for example. And in that way, you could reduce the size of those giant spoilers that are on the back there that we didn't even consider in this analysis. We didn't consider the frontal airports, minor point, but that could change the flow field there. It's worth pointing out again that these features, these fine flow perturbing features, they act in concert. They act in a holistic way. So one or more of these features that we're seeing as discrete things in our minds are actually sort of an ecosystem, if you will, of features that work together to reduce the drag. So if you were to say to implement only half of those features, you might get only 10% of the benefit remaining. I haven't tested out that theory, but generally I've seen that to be the case in at least in topology optimization structures. It's often like that. Worth also pointing out that absolute performance numbers are pretty meaningless in this analysis just because of the crude starting geometry and all that. But the percentage gains are meaningful because they're a difference between start and end. And so that makes the adjoint solver somewhat robust because you end up always doing a comparative analysis between two similar models. So you're comparing A to B as it's going along and marching through the adjoint cycles. Okay, so that brings us to our last example. Just looking at a rocket. So the drag on a rocket, pretty simple structure, pretty axisymmetric. I've modeled it as 3D in this case. Just the nose cone and 4 meters of body are included. And yeah, pretty basic model, but the physics are pretty complicated. Conditions, Mach 1 flight at 11 kilometers, so right at the tropopause boundary roughly. And again, just adjoint minimizing drag. I kept it pretty simple in these examples. Again, I have other examples about like maximizing liftover drag and stuff, but I found this to be more relevant and interesting today. So what are we gonna do? We're gonna minimize drag. Okay, so this curve shows how the drag changes with the adjoint cycles. Each adjoint cycle is marked by one of these bumps here in the drag curve. And that's just, that bump is coming from the flow solver having a rough idea of the starting conditions at the beginning of each cycle after it changes the geometry and then having to converge down. This curve looks like it's decreasing a lot and then tapering off, but it's actually, if you look at the scale down here, that's not 0. So the actual change is only about 6% from this starting point to this end point here. So only about 6%. That's a way more modest gain than I was expecting, I suppose. And also yeah, it just didn't have as much effect as I was expecting compared to the other examples. But I think that's because the geometry is already optimized for these conditions. So I think I guessed the initial conditions, the flight conditions of this structure well enough that that the actual geometry was also already optimal. But 6% gain is still 6% gain, and it's still interesting to look at the results. Yeah, so let's just focus on the red curve and the blue curve. So those are the rocket profiles for the optimized and original geometries. So blue is original and red is optimized. So again, we see this situation where, or this result where you have these sort of smaller radii joined by linear segments or roughly linear segments. I found that kind of interesting to see again. Maybe I'm trying to simplify things in my mind too much, but I am seeing a pattern there. Yeah, I mean, it's a pretty subtle change. You've got a bit of a reduction in the payload volume here, I'd say, but a bit of an increase here as well. So there's a change in shape there for the payload as far as from a design perspective. Yeah. Yeah, and at the back, it sort of rounds out and has this very large sort of subtle bulge that's going back to until it sort of rejoins the old profile. Quite interesting. But I think it's even more interesting to look at the flow fields that result. So on the left, we have the original, on the right, the adjoint solution. And you can see that sort of gradual bulge contour graphically here, even though it's pretty subtle. You can also see this straight region here as well. So on the body of the rocket, again, I've got pressures, and at the center line here, I've got Mach number, so the velocity. And you can see how this nascent shock wave that's forming on the original geometry is somewhat deflated and smoothed out by the adjoint geometry. You see the actual absolute value of the Mach number there is lower in this on this side than on the original geometry, which is substantially higher. So I suppose that's where the 6% gain is primarily coming from. Just to show you those sensitivity vectors that we interpret as displacements. So this shows 3 different applications of that, 3 different adjoint cycles. You can see that they're primarily axisymmetric, but a little bit confused, not quite perfect. But that's okay, because in aggregate, the shape that you end up with is the sum of all of these cycles as it's being applied. And you can see that later cycles tend to, or it seems like they're tending to sort of correct any anti-axis symmetry that may have occurred in earlier cycles. And again, this is like reducing gain. So you can see that at the beginning, it's very confident. It's got this lion's mane of displacement vectors that it wants to apply. Whereas in later iterations, it's kind of struggling to find where to push the boundary. Well, I thought, yeah, that's well and good, but what would happen if we do something to break the mold? Let's just put this geometry going Mach 5 at sea level and see what comes out. And what came out was interesting, definitely unintuitive. The primary changes to the structure were in the nose, just right at the tip. And it ended up making a dent in the tip. I didn't expect that. I expected it to either get sharper or I'm not sure what. But it ended up making this sort of fish lip structure. And not only that, but it made it somewhat asymmetric, which probably from a design perspective, overall vehicle performance, you don't want that. But I'm not sure how much of the drag reduction came from that asymmetry, because I haven't sort of taken this and modeled it in SolidWorks and then re-imported it in a nice clean axisymmetric way. But quite interesting to see. So ended up with about a 17% drop in drag there. Again, this analysis is pretty bogus because the flight conditions are so crazy, but you know, that dented in tip shape, maybe there's something to that. Could be worth exploring a little more. Yeah, when I was running this, I didn't really anticipate this well. So the mesh refinement there at the front was pretty, ended up pretty coarse for the level of curvature that occurred there. So you can see there's some obvious mesh dependent artifacts in the flow field. That's not so great. And, you know, could have been part of what contributed to the drop in drag, not really clear without further study. But the point here is that sometimes you have to either anticipate where the adjoint solver is going to, you know, introduce a tight curvature, or you have to rerun it with a finer mesh in that region to get it right. So this is a video of that Mach 5 run, just the beginning of it just to show how the flow field develops and how the thermal situation is changing. Now, the thermals on this are really hot just because Mach 5 with a structure like this at sea level is going to get hot. This is more just to show the progression of the solution. So this is a non-converged solution so far. You can see the thermal solution over here. This yellow curve is still converging and eventually settling down into a reasonable steady state. And then each of these bumps that's coming along is a change to the geometry. So I don't know if you can see it, but here at the front, at the nose, I'll play it again, hang on. So here at the front at the nose, you can see it's gotten more blunt. Just to give you an idea. And this is a fairly coarse mesh, but I think it was adequate for the purpose. So that's heating up and then settling into a steady state thermal solution and then perturbing that solution. So I also tried to run a case here where I base the adjoint optimizer on an objective function of average temperature, so minimizing the average temperature at the surface of the rocket, but that didn't go so well. I think numerically there were just problems there with the deriving the adjoint connection between the temperature field and the temperature average and the aero surface shape. Oops, hang on. Sorry. Okay. So in summary, we looked at 3 aerostructures optimized just to reduce drag. It's an iterative process where each iteration depends on the last, so it's a progressive solution that builds on its prior success. There are other objective functions possible. You might not realize the full gains that the adjoint solver reports if you don't implement all of those fine features. And interesting, novel, drag reducing features can arise, which I find the most intriguing of all is kind of interpreting and speculating about what effect those might have and possibly applying those ideas to other types of structure. Found that quite interesting. So I guess I'll respond to questions now. If you've typed them into the chat, or if you want to type questions into the chat, we can do that, or we could do it orally. I'm not sure, Hemi, what you want to do.
Yeah, thanks, Kava. That was
Sure.
that was a super interesting presentation. Looks like we've got a question from Gaetano. So if you just want to unmute yourself, Gaetano, ask away.
Good morning, Kava. First of all, great to see another Boilermaker down under.
Yeah, sure, great.
And we can catch up later on that if you want.
Yeah.
You kind of alluded to it in your rocket example, but does this optimization technique require generically higher mesh densities to be effective compared to other previously used optimization techniques?
I would say not necessarily. I would actually tend to say it's the opposite, because what you're doing is as the optimizer goes, it's comparing, it's calculating those sensitivities on the mesh. So I suppose you could say that if you want to develop features that are finer than if you want fine features, you can go for a fine mesh. But if you're after just kind of global, larger scale changes to the structure, you don't have to go fine.
Okay, that makes sense. Thank you.
Sure. Yeah, and I'll just elaborate on that a little bit in that in an optimization like this, you're not really targeting like an exact solution. It's not like you're looking for matching up flight test data or even wind tunnel test data. So you don't have to be quite as accurate with these sims, because what they do is they're just taking the physics that, yes, you want the mesh to be fine enough to represent the physics, but it doesn't have to be perfect, because the trends that it extracts are going to apply in a somewhat mesh agnostic way.
Oh, thanks, Kava. Question here from Dan Retief. Would the solver find the dimpled golf ball solution starting with the smooth balls?
That's a great question. I think one thing about that solution is that maybe it would find an even better solution. I'm not sure. It seems difficult to analyze though, because in the case of a golf ball, you've got this sort of periodic symmetry on the surface of the ball. I don't have a way to constrain the solver to solve for that. I suppose you might be able to get a similar solution if you put spin on the ball, but then again, even there, you've got spin about a fixed axis, so it's not going to figure out that it needs to distribute that in a regular way. So I don't think you'd get the same solution, but you might get some interesting ridged solution there on a non-spinning ball. And if you were spinning, you might get some sort of axisymmetric solution or anti-axisymmetric solution on the spinning mesh, but would be quite difficult and challenging. So I think no. I think the answer is no. You wouldn't get that solution.
Interesting. All right, a couple from Jamie Simmons here. Is there a need to verify the CFD model is correct before using the adjoint solver to ensure that the adjoint solver is morphing the shape for the correct real life environment? Example being comparison to wind tunnel data.
Yeah, I think I covered that already a little bit. I think I haven't done any validation on these solutions yet, so I can't speak to that so confidently, but my intuition is that if you've got the flow field roughly correct, then the adjoint solver is going to find a solution that's fairly robust for a variety of different mesh conditions, which are, obviously just a modeling artifact, but also flow conditions. So just from what I've seen so far, it tends to produce fairly robust solutions. I haven't done any real validation of those solutions yet. And I don't have the facilities to do that, but I would definitely be interested in cooperation if anyone does.
And another one from Jamie, with the hard to manufacture geometries that the adjoint solver produces, would you say that the predominant benefit of the adjoint solver is to identify possible areas in the model to change and what kind of geometries to change it into for aerodynamic benefits?
Yeah, I mean, that's a good point. It's a tough sell to the manufacturing side and from a practical standpoint, but there were a couple examples in here that we saw. For example, let's go to this slide here. You can see that the leading edge shape on this Wedgetail, that's a concept, right? I mean, you wouldn't have to introduce that wrinkly sort of 3D nature to it if you didn't want to. It'd be interesting to test out the effectiveness of having a constant profile with this optimized slice shape, because all of the slices were roughly the same in terms of this shape. They just looked wrinkly when you go and look at it in 3D. So, that's an example where you can interpret the results and simplify them and probably still maintain some benefit there. But again, I think the benefit might drop off more quickly than you'd expect if you simplify the geometry, or if you go for a sort of relofting approach where you reloft the surface and leave out those finer features. I guess it's worth also pointing out that for smaller structures, smaller metallic structures in specifically, you could take a 3D printing approach, and in that case, the geometry could be arbitrarily complex and would be a great thing to test out.
Yes, very interesting stuff. All right, that's all the questions we have at the moment, unless anyone wants to do a last minute raise of the hand. But I think you've covered everything in quite some detail, so we're probably good there.
Okay, great. Yeah, I guess I'd just mention again that if anyone wants to try applying this and wants some help with that, just give me a ring.